Okay, we'll start to take a look at Chapter 2. And here are the main topics from Chapter 2. Well, we're going to look at phase boundaries in the PVT surface, the pressure, specific volume, temperature surface. Phase boundaries are just like the boundaries, between our different phases that we looked at, our liquid and solid and our vapor. We'll then take a look at two-phase states, something where you have, we can think about a system or a mixture, where that we have two phases with underneath the same like pressure and temperature. You can think about it like, let's say you have a glass of ice water, right, where you have solid and liquid together. The next is liquid and solid states, where essentially a liquid is, you can think of a liquid as a state of matter where it conforms to the shape of its container, where the volume doesn't change. Okay, and a solid, of course, has a fixed structure, or that is a fixed shape, and it it has a fixed volume also. Okay, then we'll discuss superheated vapors or vapor states. And you could just think about it as essentially, you have a vapor that's higher than the saturation temperature. You can think about that as being a superheated vapor. Okay, then we'll look at ideal gas states. You can think about, ideal gas is a gas that follows all the gas laws under all conditions where you have, for all temperatures and pressures. The next is compressibility factor, and basically a way to describe deviation of a real gas from an ideal gas. Then we'll take a look at equations of state. Okay, and a simple example of this is the ideal gas law, which is pressure volume equals RT. So pressure times volume equals universal gas constant times the temperature. Okay. Then we'll look at some of the computerized tables at the end of the textbook in Appendix B. Now here's a basic example with phase boundaries in the PVT surface to start with. Okay, we'll look at this just from a two-dimensional perspective right now, or just a pressure versus temperature. Okay, so what do we have? We start off with some liquid water, add heat to this system, and our first state is just all liquid. Water's all liquid. The second state is now we've reached a point where some of the liquid has turned to vapor. And then the third state essentially is when we have everything in the same phase here. Okay. All right. So if we look at these, label them A, B, and C, we can go and plot these on the graph. Okay. Now it actually has a couple of other points here, but we'll just kind of look at or focus on A, B, and C. Okay. So for our pressure temperature, one of the things we notice is that it's a constant pressure because we have essentially the same weight on top of the piston here. So with that in mind, we're going to draw a line that's essentially the same, along the same pressure, right? And what we're going to notice is that we add more heat. The temperature is what's increasing. Okay, so we're going off to the right. Right. The first state here is just all liquid water. We add more heat. Eventually, get to a point here where you have both liquid and vapor. And heat, with additional heat, essentially get over to the next point where you're actually inside of the entirely vapor region. Okay, so this gives you just a basic example of using the pressure temperature diagram and how it relates to a basic system like this, where you have a constant pressure. Now, if we keep repeating this experiment for lower and lower pressures, what we'll see is some additional behavior here. If we look over at the PT curve, we can define some new lines or some new boundaries. Okay, we have the sublimation line. That's for when you go from a solid to a vapor directly, where you don't have that intermediate liquid phase. We have fusion line, where you go from a solid to a liquid. It's the boundary. And the vaporization curve, which essentially is anything beyond this triple point, which separates the liquid and the vapor states. Now, just looking at the curves, we're going to have P is equal to saturation pressure, or you can write it this way: temperature is equal to saturation pressure, saturation temperature at a particular pressure, or as a function of pressure. And any point on the curve is a P saturation temperature saturation point. Okay. I always have some additional terminology, superheated vapor or expanded vapor, and these two, of course, we can think about them in state A. So you can think about this like the superheated vapor essentially is saying here that the temperature is greater than the saturation temperature. So basically going from, here would be the saturation temperature at a particular pressure for the same value of P. And the others is expanded vapor, where you have the pressure is less than the saturation pressure. So like essentially from this point down for the same T, same value of T. Okay. Okay, so for the same thing as for like state B, you can think pressure is greater than the saturation pressure, so going up in this direction. And then subcooled liquid is for temperature less than the saturation temperature, and going in this direction here. All right. Then the next is a table where you could find like the critical point and the triple point data. Okay, so we'll look at that triple point for now. Basically, it's saying that where you can have, essentially all three phases together. And the pressure that's defined is this over here, kilopascals, and the temperature in degrees C. Okay, pretty close to 0. And this one is essentially 600 pascals. Okay. The other point to make out of this is that any point on the curve, basically it says like the saturation temperature pressure. In the next slide we have phase boundaries, and we actually have a PT surface here. And just things to note that on the left hand side we have a logarithmic scale for the pressure for both diagrams, and this allows us to get a larger scale for that. This is done for both water and carbon dioxide. And the other thing you'll notice for high pressures is actually additional forms of ice that are created. Okay. Okay, for this plot, we're going to refer back to our experiment when we had a cylinder filled with water, and we added heat to the system. And as we added more and more heat, the water basically turned over from vapor to a liquid vapor combination or a mixture, and then to a completely vapor. Okay. Now throughout, as each time this experiment is performed, the pressure is maintained, it's constant. Okay, meaning that essentially you had a fixed amount of weight for each of these lines or each of these curves. Okay, so we would define these essentially as like the isobaric lines, isobaric meaning constant pressure. Okay, so in this case there were 5 separate experiments performed. All right, so what happens, you add heat, you get a little bit of volume increase as the temperature of the water inside the enclosed enclosure increases, and then you get to a point here at the saturated liquid line that you start to the water starts to change phase and becomes vapor. And while that's occurring, you don't have any increase. you're just, all the energy is basically being used to change phase. You don't have any increase in the temperature. And then you start to go off to the right, okay, on this line. So the volume, the specific volume increases as you go off to the right. You get to a certain point. At this point here, all of the liquid has been turned to vapor. And now the temperature, now you have you have vapor or superheated vapor. And you start to, the temperature increases and the volume, as volume increases, okay? So you get that temperature increase as you're adding more heat, okay? Okay, now we'll take a look at a PVT surface, the pressure, specific volume, temperature surface. And these are just some notes for that initially. You know, small V's are going to be liquid or solid. Large V's are, large specific volumes are for vapors or gas, okay? There's different two-phase regions you can see here from the different areas. Here's liquid vapor. Here's a, let's see, D is the solid liquid region, and then the CB is a solid vapor, okay? Two-state region, or two-phase region, I should say. Okay. Now looking at the plot, you can actually see the PT phase diagram. We're looking at it sort of like a 2D version of it. And then you can look at it for the temperature specific volume. So if you look like straight down, what you're going to see is T, this is T off in this direction, and V off in this direction, specific volume. Now if you look at it from the right along the x-axis, so if you're kind of over here looking over this way into it, you'll see pressure and temperature, okay? And then looking in from the left, you see the PV diagram. Or you can think about it as like sort of from the front here. That's what they mean by here, okay? Now, for the most part, you know, we're going to use 2D figures or projections for simplicity, right? This is harder to actually, potentially it's harder to visualize actually what's happening at the different points, okay? Now for this surface, we're looking at other substances other than water. Specifically, this is for CO2. And if we go and look at the pressure versus temperature plot, what we'll see is that our fusion line is actually has a positive slope in this case, and for water it has a negative slope. And this is essentially due to water having a higher specific volume for a solid than a liquid, okay? Well, most other substances behave just the opposite of that, okay? Now taking a look at the water tables in section B in the textbook, and how we can actually go and translate that to a couple of different curves. The first one here is the entry point, is just the temperature, and then you have, for that specific temperature, you have the saturation temperatures, saturated liquid specific volume, the saturated vapor specific volume, and for now that's all we're going to look at. And then if we take these and we plot temperature versus specific volume, we'll end up with a curve of this shape where we have the liquid region on the left, liquid plus vapor in between here, inside underneath the plot, the dome, and to the right we have the vapor region, okay? Now over here to the right, if we plot the pressure versus temperature, we could use that to just draw essentially this curve starting from this point up. And what you'll find is that, you know, in the water tables, you'll find that we have at least one B1 0.1 through 1.4. We're going to have the liquid and the vapor regions identified. And both plots B1.1 and 1.2 can give you this curve. It's just a matter of, you know, what's the value that are actually being your independent variable, then the dependent variables off to the right. Okay. What you'll find is that the solids are basically in this region over here that's to the left of what is actually entered in the tables. So here's actually the saturated water table, B1.1, where the independent variables, here's the temperature, then it plots pressure and specific volume, specific vapor. Sorry, saturated liquid. Specific volume for saturated liquid and saturated vapor. Okay. And if we go down to the second table, it's down a little ways here. Here we are. Okay. Table B.1.2. Okay, so we're going to use some additional tables. In this case, the superheated vapor table and the compressed liquid table. And we're going to use these, basically we're to be given the state of water, some water states. And with that information, what we can do is we can actually determine the phase and the regions along the curve, or relative positions along the different curves, the TV, PT, and PV curves. Okay, so we have an example we'll go through shortly. And this provides information on like determining the going from solid to vapor directly, or the sublimation line. All right, so we'll also take a look at some problems with this. That is with this table. Okay, so here's example 2.1, and we're going to use the tables for water. And in this example, we want to determine essentially the region on the PV, TV, and PT plots for these two states of water. First one we could do is just starting from looking at table B1.1, and this table is in Appendix B. And what we could do is we can draw the curve of temperature versus saturation pressure. And when we do that, we get the curve on the left. The diagram, pressure versus temperature, and here's the curve right here. Okay. For the next plot, pressure versus specific volume, we can then go into the same table here if we want, or we could go to the B.1.2 table. But in this case, we're looking for the pressure. So we have the pressures, and we're going to plot the saturated liquid line and the saturated vapor lines. And for the third plot, the temperature versus specific volume, we could create the same plot here, except now we're looking at specific volume as a function of temperature. So we're getting entries of temperature here, and then we're basically creating two curves that meeting at the critical point, where you have the temperature versus specific volume for saturated liquid and specific volume for saturated vapor. And that's how you would draw basically this blue curve. Okay. And you know, we have our different regions. Here's our liquid, here's our vapor. Over here we have liquid over here and vapor over here. In here you actually have a combination or a mixture of both liquid and vapor, and the same thing in this region. Okay, so we have our liquid over here, liquid vapor mixture in the middle, and then vapor over to the right. To come up with those isobaric lines, you could actually go into table B.1.3 superheated water vapor, and here now it's broken up by pressures. Okay, so you would see how you could create those lines. So this one shows two different pressures here. One is at 198 kilopascals and the other is at 500 kilopascals. The other choice here, of course, is if you just draw a straight line, so you have this specific volume at this pressure, and the specific volume ranges between here and here for for those defined pressures. Okay, the saturated liquid point and the saturated vapor point. Okay, so those you could just draw a straight line between those. Probably be an easier way to do it. So we have the general curves here defined, and if we look in, depending upon which table we look in and what information it gives you, both cases we have a liquid. And if you just start with B.1.1 and you enter the temperature and you enter the pressure given, what you're going to find is that the point that you see is going to be on the to the left essentially of the saturation curve. Okay, so since it's to the left of it, it's going to be it's in the liquid state or liquid phase. And you could do the same thing for the other plots. You'll notice it's to the left over here, point A, which is problem A, and to the left of the temperature specific volume plot over here. Okay, so it's just by itself. In part B, or problem 2.1b, we have a temperature 120 degrees, and we're given a specific volume. So if we look at that value again, we see it's 0.5 meters cubed per kilogram. So if we look and the temperature is 120 degrees C. So if we look at that entry here, 120 degrees, we go off to the right and we look at that specific volume, what we find, it's between the saturated liquid point and the saturated vapor point. So we know that for that one, for 120 degrees, we're in this region where we have a mixture, saturated liquid and vapor, or we have liquid vapor mixture in that point. Okay, now we're going to look at two-phase states, and in this case we're going to look at a liquid that's in equilibrium with some vapor. Okay, so in some enclosed volume. Right. So basic idea, we start off with total volume of this, and our end goal from this is to come up with an equation that represents the average specific volume of this mixture. Okay. So we start off with the volume of the liquid plus volume of the gas, gives us the total volume in here. And we can rewrite that as the mass of liquid times specific volume times the mass of gas times specific volume of gas. And of course the mass is what's in liquid and what's gas. To come up with the average specific volume, you're just going to take the volume and divide it by the total mass. Okay, so then what that ends up happening is you have a ratio of the mass that's a liquid, and the ratio of the mass that is a gas or vapor. Okay. Now, if you go with the derivation, your equation would come up to be, which I'll do shortly. It's going to come up to be 1 minus x Vf plus x Vg. Okay. And then if you use, well, you have to use this substitution for x to come up with x here. But then if you use this define Vfg as just a specific volume of gas minus the specific volume of liquid, you can come up with a final form of this equation as a function of this x. All right. And then, okay, where we have this x is the x is the mass fraction of vapor, and then 1 minus x is the mass fraction of the liquid. Okay, so now we'll take a look at where this equation comes from, some more details on that. We have, in this case, we have average specific volume, which is total volume over mass, and then the ratios as before, ratio of the mass that's liquid times the saturation specific volume for liquid and saturation specific volume for gas times the ratio there. Okay. Well, I'll make a couple substitutions. One is the mass of liquid portion is just total minus the mass of the gas. Okay. So with that in mind, we can make this substitution mf over m just equal to m minus mg over m, right? So here's that first equation with that substitution, okay? Now if we break out this, just divide m by m, break up this fraction, we have basically 1 minus mg over m times v of f plus mg over m times vg, right? Now we define x as being equal to mg over m, so we just put x in here and x here, and here's our new equation. So I multiply this out, vf times 1, and then vf times minus x, and here's the new form of the equation. And then we put x over here, we divide out x from these two terms, and we have the new form here, which is x times saturation specific volume minus the saturation specific volume of vapor, saturation, that's saturation, and then just times plus v of f. So then we come up with another term, and this is actually, you'll see this on the table, specific volume of the difference between gas, the saturation points between gas and liquid, okay? And with that substitution, we can rewrite this in this form. Okay, so this is like the final form, right? And that's basically it. So this is just brief overview of where this equation is coming from. There were some steps missing on the slides. Okay, so here's another example. It's actually using the quantity we had with the previous example, 2.1b. So in this case, we have what's defined is we have a temperature and a volume, okay, or specific volume in this case. So what we're going to do is try to determine how much of this is vapor, all right? So we can do that just starting off by, looking in our saturated water table at 120 degrees. And we do that, and we can find out some information. We can find out specific volume for our saturated liquid, and we can find it for specific volume for our saturated vapor. Okay, so we start off with an equation for average specific volume, and we just rewrite it. So we're looking for this quantity x, and from there, determining what x is we have our volume, which was given, and we have the specific volume for our liquid, and we divide it by our specific volume, the difference between the specific volume for gas and liquid, which is right here. Okay, just the difference between these two essentially. And then with that information, we can write it as, the volume of gas divided by the total volume. And here's just another way to represent that, mass times the specific volume for gas, and which is just the mass times the specific volume that was given, okay? So mg over m is just x, which we defined previously, and then we just have specific volume of gas divided by v, which is our average specific volume here, which was given. All right. So when we rewrite this, we put in Vg, we multiply it times our x over 0.5, and this gives you the ratio of it. That's that tells you the percentage of this, of the volume of the fraction of that's vapor, or the volume fraction that's vapor, okay? And this says, okay, here's the vapor, total volume that's vapor, divided by vapor, which we previously looked at. All right, so you solve for that, and you find out 98.89% essentially, okay? So in terms of volume, it's almost all gas, right? And it gives you an idea how much less dense it is in terms of the volume for liquid and gas. So 56% of the total, which we showed here, is actually vapor, and then 99.89% It takes up 99.89% of the total volume. All right, and that's it.